All right, let's jump right in and tackle a real classic physics problem. What happens when you push something, but the force you're using is constantly spinning around? It sounds like a total headache, I know, but the way we're going to solve it is actually a fundamental tool you can use for almost any problem with vectors. And once you get this down, you're going to see physics in a whole new light.
Now, this particular puzzle comes from a legendary and famously difficult textbook by I.E. Irodov. If you've ever seen this book, you know it does not mess around. So if this problem looks intimidating to you, hey, you're in good company. But don't you worry, we're going to break it down and walk through it together, step by step.
Okay, so here's the official problem. We've got a particle just sitting there, not moving. Then we apply a force, F. Now, the strength of this force is always the same, but its direction is constantly rotating, spinning around at a steady rate we call omega. I want you to picture a little arrow that's pushing this particle, and that arrow is just spinning and spinning. Our mission is to figure out its velocity over time, and then find out how far it goes between the moments it stops.
I know, right? Just reading that can make your head spin. But trust me, the secret to cracking problems like this isn't about being some kind of math wizard. It's about having a clear, logical plan of attack. So let's build one together.
Before we write a single equation, and this is the most important step, we need to get a really clear picture in our minds of what's going on. What is this particle actually doing? Let's just visualize the whole scenario.
So here's the real heart of the problem. Newton's second law, our good old friend F equals ma, is super easy to use when the force F is just pointing in one direction. But what are we supposed to do when that F is constantly changing where it's pointing? We can't just plug it into the equation. We need a way to deal with a vector that just won't sit still.
And here is our game plan. This is a super reliable strategy in physics. You're going to use it all the time. First, we're going to lay down an XY coordinate system. Second, we'll use a little bit of trigonometry to break that spinning force down into its x and y pieces. Third, we'll apply F equals ma to the x direction and the y direction separately. And finally, we'll use some calculus and integrate to get the velocity. Simple as that.
All right, we have our roadmap. Now it's time to actually do the math. But remember, we're not just throwing equations around randomly. We're following our four-step plan. So, first up, let's break that rotating force into its x and y components.
And this right here, this is the magic trick. By saying the angle of the force at any time t is just omega times t, we can use cosine to describe the x part of the force and sine for the y part. So we've taken one really hard 2D problem and split it into two much easier 1D problems. That's a huge win.
Okay, so what we have now are basically the equations for acceleration in each direction, since acceleration is just force divided by mass. But we want velocity. So how do we go backwards from acceleration to velocity? We have to do the opposite of a derivative. We have to integrate.
Let's start with the x direction. We're integrating f over m times cosine of omega t. Well, the integral of cosine is just sine, and because of that little omega inside, it's like the chain rule in reverse, we have to divide by it. So that gives us vx. Now, there's always a constant of integration, right? But the problem told us the particle starts from rest, so at time t equals 0, vx is 0. Since sine of 0 is 0, our constant has to be 0 too. Easy.
Now for the y component. And pay attention here, because this is a classic spot to make a mistake. The integral of sine is negative cosine, so we get a negative f over m omega times cosine, plus a constant. Again, we use our starting condition. At t equals 0, vy is 0. But wait, cosine of 0 is 1. So, to make the whole thing 0, our constant c has to be positive f over m omega. When we factor that out, we get this classic and very important 1 minus cosine form.
Fantastic! We've got our separate velocity components, vx and vy. To get the total speed, which is just the magnitude of the velocity, we put them back together using the Pythagorean theorem. Square them, add them up, and take the square root.
Now, if you were to actually plug our expressions for v sub x and v sub y into that square root, you'd get a big, ugly mess. But, physics often hides some real elegance inside all that complexity. A super handy trigonometric identity comes to our rescue here and cleans the whole thing up beautifully.
And there it is, the answer to part A. Look at that, it's a beautiful, simple equation for the particle's speed at any time. But look really closely. You see those absolute value bars around the sine function? That is the most important part. It tells us speed can't be negative, which, duh, of course. But it also tells us that the speed is going to periodically drop all the way down to 0,
And that is the key to the entire second half of this puzzle.
So we've done the math, but the math is just a language, right? We need to translate it. What is the physical story this equation is telling us? Getting from the equation to what's actually happening is the whole point of physics.
So let's really think about this. The speed is basically controlled by this absolute value of sine. We know sine bounces between -1 and 1, so the absolute value of sine is going to bounce between 0 and 1. This means our particle is constantly speeding up and slowing down. So when does it actually stop?
Well, the particle stops when its speed is 0, and that happens whenever that sine term is 0. For that to happen, the stuff inside it, omega t over 2, has to be 0, or pi, or 2 pi, and so on. So the first stop is at t equals 0, which we already knew. The next one happens when omega t over 2 equals pi, which means t is 2 pi over omega. The stop after that is at 4 pi over omega. You see the pattern? The time between any two stops is always the same, 2 pi over omega.
Perfect. We've totally cracked part A and we used it to figure out the time between stops. Now we can use everything we've built to go after part B, finding the distance it travels in one of those cycles.
This should look familiar. Just like we integrated acceleration to get velocity, we can integrate speed to get the total distance traveled. So we're going to set up an integral of our speed equation, v of t, and we'll integrate from one stop at t equals 0 to the very next stop at t equals 2 pi over omega.
And when you do that integral, after all the dust settles, you get this, a surprisingly simple and clean result. The total distance the particle travels between any two stops is just 8 times the force, divided by the mass times omega squared. All that calculus for such a neat little answer.
And the very last piece of the puzzle is the mean velocity. This part's a piece of cake. It's just the total distance we just found divided by the total time it took, which we already know is 2 pi over omega. You do a little bit of cancellation, and there's your final answer.
And there you have it. We have completely solved this beast of a problem. But honestly, the answer itself isn't the point. The real goal was to build a reusable problem-solving toolkit that you can take with you and use on other tough problems.
So let's recap our strategy. First, always visualize the problem. If you see something spinning or rotating, your first thought should be components. Break it down. Then apply your physics laws, like F equals ma, to each direction like it's its own separate problem. Use calculus to climb the ladder from acceleration to velocity to position. And maybe most importantly, when you get a mathematical answer, ask yourself, what does this actually mean? What is the story it's telling me? That's your blueprint for success.
You know, we figured out so much about this particle. We know how its speed changes, we know how far it goes, but here's one last question to chew on. What does the path it traces actually look like? What shape does it draw in that plane? It turns out to be a really beautiful and famous curve in physics. But what it is? Well, that's a puzzle for next time.